Hello and welcome back to the channel. This is Castro. After a good response to my previous couple of videos, I wanted to make another one, this time focusing on the fourth and the fifth axis of this high precision machine. So without further ado, I'll strap the camera to myself and we'll have a look at the components. Okay, so since I suspect that this is going to be a relatively long video, I'll get straight to it. So on the left hand side I've got the fourth axis component, and on the right hand side I've got the fifth axis component. So let's start with the fourth axis component, right? So we've got a housing which is this big aluminium piece. This will be sitting flush on the front of the granite base, so essentially it will be like that. And on the rear side we've got the granite base. So inside we will have a torque motor and an encoder and a series of cooling elements and some sort of bearing system, which I will explain. This rear face has been lapped to a relatively flat tolerance and good flatness, so when it sits flush against that granite surface using these 4 bolts and also 2 pins, then it will have maximum contact surface. Also, this lip around the corner has been lapped with these lower parts as well. Okay, so on the front side we have this diameter, which has been machined and then jig ground to a very tight tolerance to house a bearing in here. So for the bearing on the fourth axis, I have chosen to go with this bearing. This is a cross roller bearing from THK. It's one of their super precision bearings. Actually, it's USP, which they call it ultra super precision, and then it's got extra preload, so you can see it's C0, so double C and the 0. This has a starting torque of just under a Newton meter, so it's a pretty stiff bearing. And this diameter has been ground to about 3 microns less than the diameter of this actual bearing. So a jig grinding machine, they've ground this diameter, and also this rear, this face here is also parallel to the bottom face that has been lapped. So these two are parallel, so that's been ground relative to the rear surface, and also this diameter as well. So these two are square, and this also diameter is square to the rear face as well. And then for aesthetics and also some functionality that I will mention, this front face has been ground parallel to the rear face as well. So eventually there will be an O-ring which will be around here to seal off any debris, coolant, swarf, anything that can get near this bearing. Okay, so this bearing will sit right there, and then to hold this bearing in place, it's got bolts which they're here. So it's got bolts all the way around it, and I usually avoid bolting anything to aluminium itself. So I've got this stainless steel ring which will from underneath, which will sit underneath this lip, and then the bolts will be screwed onto this, which has been tapped, right? Okay, so inside this diameter we have this part. So this is essentially the fourth axis transmission shaft. It's quite a complex part. It's been machined from one big diameter of stainless steel. It's 316L, and it's been ground almost on most surfaces basically. So this is where this bearing will sit. I believe it's this one. I think it's this diameter. That's where the bearing sits. Then it will get bolted onto the bearing as well, all the way around it. And on the rear side of this shaft, here we have an additional bearing just to support the end part of the shaft. Although these are pretty good in both axial and radial forces, because we're getting a little bit far from the bearing, I wanted to support the end bit with another bearing as well. So inside here we have a cooling ring around it, which will be installed, and then we've got two pipes that will push cooling or coolant through here all the way around the motor that we've got in here, which is, as I said, it's a direct drive motor. I think it's about 70-80 Newton meters of maximum peak power or peak torque, and I think it's the nominal is around 30 to 35 Newton meters, if I'm not mistaken. I ordered it over a year ago, so I might be a little bit off. And this is basically a lid that will close this part off. But it's got some other functionality as well. One of them is that it houses here on these little screw or tapped holes that you can see. These are for a reed head, an encoder reed head, and also that extra bearing that I said, it will sit inside this diameter. So this will go in there like that. And this whole thing sits about 0.5 millimeter below this lip that goes around, so it won't interfere with this face that is sitting against the granite. What else? Oh, right. This raised lip all the way around it. This is what is pushing the torque motor stator in place. So we've got the torque motor sitting down there in one of these diameters, and this one will basically sandwich it in between, and then it pushes it so it's locked in place and it's not rotating or going anywhere. So that's your fourth axis, I would call it. I will later on show you a sample of the torque motor. It's very similar to the C-axis one. I just didn't want to open it up. It's in a big box underneath loads of other boxes. But I'll show you one of the motors, which is for the C-axis. The A-axis is very similar, just a little bit bigger in diameter. So that's the A-axis. If you've got any questions about that, leave a comment below. I tend to answer all of you at some point. So yeah, that's the A-axis. Now let's get to the C-axis. The C-axis will be something like this. So eventually we'll have it like here. If you watch if you've watched my other videos, especially the one that I'm explaining the design on Fusion 360, then you will see all the inside of these two pieces together. So that's where that O-ring that I mentioned will sit. So we've got an O-ring here that will sit on this face. That's why it's being ground as well. Right. So what do we have in here? So a relatively similar setup really to the A-axis, although this one has a lot more tighter tolerances, especially when it comes to grinding. One of the things that's being ground is, you can see this diameter. This diameter is where this A-axis shaft will go through. Again, 2 to 3 microns below this diameter. And what it does is basically bringing this whole assembly of the C-axis to the center line of the fourth axis. So the fifth axis will be on the center line of the fourth axis. Fifth axis will be on the center line of the fourth axis. In here we've got two bearings. These are the bearings. So from FAG, Super Precision System, and these are a pair of angular contact bearings, which are like this. I think it's 30 millimeters RID and 47 OD. So we've got a pair of these which will sit inside this diameter. And so this diameter and also this lip underneath it, or on the bottom side, these have been jig ground as well. So they are pretty round, 2 to 3 microns smaller than the diameter of that one. So when we expand this and shrink those and put them inside, then it'll just grab it. And also, this diameter is perpendicular to the diameter of the connecting shaft of the 4th axis. So when it goes like that, then this one and that one, these are square. And also they are on the center line of each other as well. So this has been a pretty tricky part to design, and also much harder to manufacture and jig ground after that. Then we have a ring like this, which will basically hold these two bearings in place. So we've got these bolts that will go through this one, and then underneath we've got another stainless steel ring that essentially these two push the bearings together, creating that preload that is essential for the angular contact bearings, and also pushing them against this seating area that we've ground for them. There's also other functionality about this this ring as well. So this one, you can see there's some holes around it, and these holes they've got different diameters. Reason for that is we've got another hole here, as you can see it here, and that one is to basically pressurize this area and creating an air pocket. I believe it's around here, where it pushes away all the debris and all the coolant and everything away from the bearings and also this main part, so that nothing would seep through. And the reason for different diameters is because if you push the air from that one and then you've got very similar diameters, then all the air will come through this or that hole. But if you've got smaller diameters here and then larger diameters there, then the air would go almost equally from all of these holes. Obviously, I had to calculate some of that, the amount of space or the volume of space that I had around here, and also the pressure of the air, and also the diameter of these holes. So there has been quite a lot of calculations involved in that, but I hope it works in theory as well. I've done something similar in the past and it worked well. So yeah, that's for that. That hole has got an interesting story. So basically, it starts from here. Here we've got this hole. It's been drilled all the way down to around here. Then there's another hole that's been drilled from that way and then intersect with that one. And that hole in the back comes all the way to somewhere around here. And then we've drilled another hole up top. So that's basically creating a long pass. So we will have an air fitting in here. The air will go through there, comes up. Obviously, then it's got two ways to go. One is that way and one is that way. We will block this. So this has been tapped. We'll block this with a grub screw. So then it can only go that way and also that way up. So basically, we've created a channel of air like that. What else? These bolts are for to mount these to that bearing on the Z-axis, and these are to connect them to the shaft, and there will be pins in place as well. Okay, let's talk about the shaft, which is quite interesting for the C-axis especially. So, this is the C-axis rotating shaft. Um, so what's special about this? Obviously, it's been machined from one single piece, again, stainless steel 316L. Top face has been ground, and it's a square to this where the bearings will sit. It's got another bearing supporting the bottom part of it. So we've got those two bearings here, and then another bearing here, and then we've got a locking bolt that will tighten the whole thing and then hold it in place like that. This top face will accept a System 3R automatic chuck, and that automatic chuck is a pneumatic chuck. So how do you get air to that pneumatic chuck? So you can have a look at these holes and they might give you a clue. So what we've done is very similar to the thing that we did on the housing. We've drilled 4 holes all the way to the top, but they didn't come through from the top. So these are where the holes are. So we've drilled them all the way to the top like that. And then we drilled 4 other holes like that, basically cutting those, and then 4 other holes like that, right? I've printed an image for you so you can have a better understanding of how it works. Let me get a pen. Right, so as you can see, these are those 4 holes. Basically, they come all the way up, they go to the side, and then they come up as well. So that's basically creating an air channel, well, 4 of them, that goes right from underneath to the right and up to the chuck. And that's the System 3R chuck up there. Okay, now why did we do something like this? Reason being, if obviously this is a rotating system. So if it's rotating and you've got 1 to how many air channels, then you need to have something called a rotary union. And those are big bulky devices with some bearings and a lot of sealings around them that allows you to rotate something that is fixed on one end and is rotating on the other end, or both can be rotating at different speeds. Those are quite bulky. They have a very short lifetime because those ceilings will break, and also when you've got multiple channels, and especially if you're rotating at high speed, they can be very, very expensive and also not that much reliable. So I had a different approach to this. What I did was, as I said, I created those 4 channels, and because this system is holding the pallet where the workpiece will sit using a spring mechanism, so you can see these are the springs here. Because it's using the spring mechanism to hold the pallet in place and it only needs the air to release it, then we don't need to connect air constantly to this chuck. So what we can do is, when the system is stopped and we just want to change the pallet, we can only then connect the air to it. So underneath we've got this big pneumatic cylinder that is has a spring return, so it's only with a pneumatic air inlet, it only goes up, and then it pushes this little device against that rear face. And this little device is creating, what it does is creating 2 air channels, 2 separate air channels, because this only needs 2 air channels. 2 air channels, and pushes them pushes the air from these holes that we've created. So you can see this channel, which goes all the way around and comes here. Obviously this is a cut and a sliced section view. So this channel is pushing it up through this line and that line, and this middle one is pushing air from to these middle sections or middle channels. And then we've got two small O-rings to create a seal against this bottom face. So with that said, that means that this bottom face is ground, so it's pretty flat. Then we've got that little device that I said, which will eventually have a couple of O-rings in it, and then it sits against this flush, and then it's got two inlets for air, two separate channels of air. Again, similar system. So we drilled a hole like that, and another one like that, and then another one like that, another one like that. So we've got two air channels, right? So when we want to change the pallet, obviously this is stopped. We activate this cylinder, goes up, create a seal, and then we can blow air through these two channels. They go all the way up there to the side and up, and then they release the chuck. Got that? Obviously we will block these four side holes with grub screws, and I will also use them to put some weight, and then when we want to balance the whole thing, we can use these four grub screws to balance and minimize vibrations on this axis as well. Okay, so this has been a very tricky part to make, and also after all of those drilling and whatever we had to grind it to size as well. So a very interesting part. I'm quite proud of how it turned out. Okay, so we've got that and we've got that. So on this one, you can see how it works. So these are the bearings. This is the ring that pushes them together. This is the ring that's got all the tapped holes. Then we've got the torque motor, the stator, the rotor. Then we've got these two little pieces, which are these just spacers. Then we've got that rear bearing that I told you about. Then we've got, this is an old design, we've got one single nut, a locking nut that locks the whole thing, and it pushes all of them together, and it's basically grabbing all of that and pushing them against each other, so we can adjust the torque that is needed for these two bearings. Then underneath we've got that device, which is that one. Then we've got this pancake, I call it a pancake pneumatic cylinder. This is from a company called Bimba, which is, I think they are American. Very good quality stuff. It is relatively expensive for what it is, but I couldn't find anything similar to this quality and the size I needed. Then we've got the cooling jack, which is, or the cooling channel, which goes around the stator, and it cools down both the structure of the fifth axis and also the stator itself. And then we've got these lines of all the cables and everything that goes out. Here you can see this is the disc for the encoder, and that's the encoder read head right there, which I'll show you those parts as well. Ideally, in an ideal world, you want to have all of these cables and lines to go through the fourth axis, but we didn't have enough space, and we had a big hollow for the fourth axis, and we could have fitted all of them cables through that. But the reason that I say we don't have enough space is that we didn't have enough length. So when you twist these cables day in, day out, obviously they will break eventually. You are basically creating tightness in between these motions, and basically these cables at some point they will start to crack and snap, and we've got hoses as well. That's why we opted for a less desirable way, but a more practical way, which was having the cables to feed through a big gland and a conduit. So that's where the cables will go through eventually, and it's got its own bearing with 90 degrees of movement. Okay, and then we've got a transparent, which I will probably 3D print this lid, which only just seals the whole thing off, and then creates a little seal, and also allows me to see the mechanism inside when this is moving, so you can keep an eye out for any failures that might happen inside this. What I have not showed you is this part, which is just going to sit there like that, and very similar to the 4th axis setup. This will push the C-axis stator or the 5th axis stator in place, and it grabs it and holds it in place. It houses the encoder, so that's the encoder read head where it goes, and then also the bearing that I said will go and will sit on inside this diameter. And last thing to show you is the C-axis motor. So this is the rotor itself with all the magnets. This is from a company called CPC, Taiwanese, really good quality products. I've used their products in the past. So the 4th and 5th axis direct drives, which have been purposely built for my application with the figures that I told them. So these are custom built, and that's the stator for the C-axis, which will go inside there. And this is the test sheet for this one with all the dimensions and also the torque figures. This can go up to 7,000 something RPM, I believe, so 7,500 RPM. I intend to rotate this as a maximum of 4,000 to 5,000 RPM. And yeah. And then this has got a pretty good torque value in lower RPMs as well. I think up to 35 Newton or 40 Newton meters at peak, 35. So it's pretty good values for a small C-axis setup like that. So yeah, direct drive motor, and then the stator as well, which that was the stator. This is the rotor. What I need to show you now, lastly, before we call it a day, is the encoder. So that's the encoder read head, which is this little fella. Hope you can see it. It's just a PCB with a little bit of a flat cable. So this will be mounted in there. It's an optical encoder. I forgot how many bits. I think the accuracy that I was getting for the diameter of what I have was, I think, less than half an arc second, something like that. But I have to double check. I believe when I checked it and I converted it into millimeters in a diameter of 150 millimeters, that small distance with the accuracy of this encoder was about 0.2 microns. So it's pretty accurate. It's not as accurate as the 50 nanometer scales that I've got for the X, Y, and Z axis, but still pretty accurate, 0.2 micron is pretty good. And this is the encoder disc itself. I'll probably remove these gloves because I'm not sure how clean they are. So it's basically a 1 millimeter glass disc with loads of little lines on it. And then we will glue that to this, to basically this face. And yeah, that's it really. There's another one very exactly same for the 4th axis. So I hope you like this video. Please consider subscribing to the channel. It really encourages me to create more videos for you. And then if you've got any questions, ideas about what you want to see in the future videos, please leave comments down below in the comment section. And I will leave a link to my Instagram page as well, where I usually post stories or reels about various small updates about the project. So yeah, leave your questions down below. Make sure to subscribe to the channel, and I hope to catch you in the next one. See you later.